Okay, so today let us discuss the Cartesian system in two-dimensional geometry. Mainly if we coming to the point of this Cartesian system, we can consider two types of systems in which the rectangle, the axis x and y axis in this system are not perpendicular to each other, they are inclined at an angle of some omega which is not a right angle. This type of system is called oblique system, in which the entire geometrical properties we develop with the help of these x coordinate, y coordinate which are associated with this omega angle. Now to make it more simplified way, this oblique system is converted into rectangular Cartesian system by taking this omega equals to 90 degrees. In particular case omega 90 degrees, we just take this as rectangular Cartesian system in which axes are perpendicular to each other. Here, with reference to this rectangular Cartesian axis, to locate any point in this, we define its x and y coordinates. Suppose if px comma y is a point in this Cartesian plane, then the perpendicular distance from algebraic distance from y axis, this is taken as its abscissa, and this is taken as algebraic distance from x axis is defined as its y coordinate or simply ordinate. In case if the point is in third quadrant, this abscissa as well as ordinate both will become negative values, because they are lying on left and below the left side of y axis as well as left side of the x axis, both will become negative. So like this, depending on the quadrant, we choose the appropriate signs for the coordinates here, x and y coordinates. In first quadrant, we take both of them positive because x is positive, y is positive, and in second quadrant we take x coordinate negative, y coordinate positive. In third quadrant both are negative, and in fourth quadrant x coordinate is positive, y coordinate will become negative. Like this, we just decide the signs of a point in different axes, different quadrants. Not only this, if a point is lying on x axis somewhere, on x axis y coordinate will be treated as 0. Anywhere on this x coordinate, x axis, y coordinate is 0. That is why we consider y equal to 0 as x axis equation. In similar way, on y axis anywhere if we choose a point, its abscissa is 0. All these points will be taken x coordinate 0. That's why now onwards we consider x equal to 0 as equation of y axis. Therefore, equation of x and y axis are respectively y equals to 0 and x equal to 0. Once we know how to locate a point and how to take the coordinate signs in different quadrants and even on coordinate axis, based on this, now let us see how to develop some more properties in this basic coordinate system. In a Cartesian system, rectangular Cartesian system, suppose we have 2 points given x1 comma y1, b x2 comma y2. Now let us get a relation for getting a point which is dividing this in the ratio of some m is to n. If AB is a line segment on which P x comma y is a point which is dividing these in the ratio of m is to n internally. Now we have to get the coordinates of this point which is dividing these two in the ratio of m is to n. For this, just we draw projections from A, B and P on x axis respectively. A dash, P dash B B dash. Now this O A dash in the diagram, O A dash is nothing but abscissa of coordinate A. O A dash is equals to x1. Similarly, O P dash will be x and O B dash will be x2. These are abscissae here. Now let us draw perpendiculars from A and B. Let us draw perpendiculars from A and P respectively on these other two lines. Suppose this is AM, this is B, this is PN. Now A dash P dash is equals to AM also here. Therefore, here AM, if we calculate AM, which is nothing but A dash P dash, A dash P dash is nothing but OP dash minus OA dash. This OP dash is x minus x1. Similarly, we can calculate Pn also. This Pn is equals to P dash B dash. This P dash B dash is equal to OB dash minus OP dash. This will be equals to x2 minus x. So we are getting this value x minus x1, this is x2 minus x. In similar way, if we take y coordinates also, we'll get in similar way here. And because triangle AMP is similar to triangle PNB, therefore AM by Pn, ratio of these two sides equals to ratio of these two sides, AP by PB. But AM is equals to x minus x1 by Pn is x2 minus x equals to AP by PB. Already we have taken this ratio as m is to n. Applying this, if you simplify this, nx minus nx1 equals to mx2 minus mx. Transferring mx left side, mx plus nx, m plus nx equals to, we get mx2 plus nx1. This implies x equals to, we get mx2 plus nx1 by m plus n. This is taken as the abscissa of the point P, which is dividing AB in the ratio of m is to n. In similar way, we can get y coordinate also equals to my2 plus ny1 by m plus n. Therefore, the coordinates of any point which is dividing A and B in the ratio of m is to n internally is mx2 plus nx1 by m plus n and my2 plus ny1 by m plus n. In similar way, if two points are divided by third point in the ratio m is to n externally, if P is dividing AB in the ratio m is to n externally, that means AP by BP equals to m is to n externally. In that case, we can get the coordinates of P as mx2 minus nx1 by m minus n, my2 minus ny1 by m minus n. This is taken as external section formula. Like this, in this derivation, we could able to derive the points which are dividing given two points in the certain ratio m is to n internally as well as externally. Now let us see how to find the ratio in which a point is dividing other two collinear points. Let us trace out. In the previous one section, ratio given, we could able to find the point. Now we are finding the ratio in which the third point is dividing the given 2 points. Suppose let us take 2 points x1 comma y1 and x2 comma y2, and somewhere here we have C x3 comma y3. Now let us find out the ratio in which this C x3 y3, which is collinear, dividing A and P. So to find out this ratio, let us assume this ratio as lambda is to 1. Of course we can take it as m is to n also. This is better way of finding the ratio. If C is dividing these two in the ratio of lambda is to 1 internally, then x3 y3 coordinates can be written as, applying section formula, lambda x2 plus 1x1 by lambda plus 1, lambda y2 plus y1 by lambda plus 1. Now on comparing the corresponding coordinates, lambda plus 1 x3 equals to lambda x2 plus x1. So lambda x3 minus lambda x2 equals to x1 minus x3. Then lambda will be x1 minus x3 by x3 minus x2. Therefore, in similar way we can take lambda value by using y coordinates also. This is also equals to y1 minus y3 by y3 minus y2 also we can prove. Therefore, 2 points x1 y1 and x2 y2 are divided by the third point x3 y3 in the ratio of C divides AB in the ratio of minus, to get it in particular order, minus difference of abscissa of first and third and second and third, or minus y1 minus y3 by y2 minus y3. This is the way of getting the point in which ratio in which a point is dividing the other 2 points. This is exactly the converse to the previous theorem. Previous theorem we could able to get the point when section ratio is given. Here conversely, when ratio is given, when point is given, how to find the ratio we are calculating here. Now let us concentrate on one more important conceptual point, harmonic conjugates. When do you get these harmonic conjugates? What are these? Let us have a look here. Suppose A, B are any 2 points in the coordinate plane where P is a point dividing AB in the ratio m is to n internally, whereas Q is another point dividing AB in the same ratio m is to n externally also. Therefore, here P and Q both are dividing AB in the same ratio, one is internally, other one is externally. Then PQ are said to be harmonic conjugates to each other with respect to AB. This is the mathematical definition for harmonic conjugates. Now let us look at these properties of harmonic conjugates also. Here, if AB are divided by PQ in the same ratio, then obviously PQ also divided by AB in the same ratio. Some m plus n is m minus n ratio, or m minus n is m plus n ratio. So the first point is, if PQ divides A and B in m:n ratio, then A and B divides P and Q in the ratio of m plus n is to m minus n or m minus n is to m plus n, depending on the case A, B positions. Second point means if PQ are harmonic conjugates to each other with respect to AB, then AB are harmonic conjugates with respect to PQ will come. Second one, starting from the first point, AP, AB and AQ are always in a harmonic progression. We can prove by using simple mathematics here. Just we can show that AP, AB and AQ, all the three are in a harmonic progression. That is why purposefully we are naming this as harmonic conjugates to each other. So in finding harmonic conjugates, in particular when 2 points are given, first we find out P dividing AB in what ratio. If it is dividing in m:n ratio externally, we calculate by using internal section formula, and if it is dividing internally, the other one will give you external ratio. Like this, first we get the section formula, based on that we get the ratio, after that we using that one we get other point also. So this is the way of finding harmonic conjugates here. Now let us concentrate on the points of concurrence of various cases in a triangle. If we choose randomly a triangle in the plane ABC, here if you join the midpoint of any one side with opposite vertex, this is called a median. So here AD, similarly BE and CF medians. If we observe in any triangle, always these three medians are concurrent at a point which is called the centroid of the triangle. This G is defined as centroid of the triangle. This is taken as the first point of concurrence. Now let us discuss in detail about each and every point of concurrence in these triangles. Here, now if we concentrate on centroid properties, here centroid always lies on the median, and also we can show that this centroid divides any median in the ratio of 2:1 internally. Median divides this triangle into two equal parts. At the same time, centroid divides median in the ratio of 2:1 ratio. So AG GD ratio or BG is to GE or CG is to GF equals to 2:1. Using this section formula 2:1 ratio, we can show that the centroid coordinates will be x1 plus x2 plus x3 by 3, y1 plus y2 plus y3 by 3. We can prove with simple section formulae centroid coordinates like this. In case if the vertices are x1 y1, x2 y2 and x3 y3. This is about centroid coordinates. Third one, let us have a look at the remaining points of the centroid also here. Now centroid divides triangle into three equal triangles. Triangle GAB, GAB, triangle GBC, triangle GCA, all are equal, and adding all the three we are getting total triangle area. That's why each triangle is 1/3 of area of triangle ABC will come back. The area of triangle formed by centroid and any two vertices is 1/3 of the total triangle ABC. Fourth one, here this triangle ABC, in this, if you choose the midpoints D, E and F, all the three midpoints if you join, we are getting four triangles in the diagram as in the diagram shown. Here triangle DEF, triangle EFA, triangle DEC, area of triangle BDF. All the four are equal. All these four triangles are equal, and each one is 1/4 of area of triangle ABC. This is another important point. Even we can guess easily what is the interrelation between this area and this area also, this triangle area. So we can get interrelation between these very comfortably. Now coming to the fifth point, here in a triangle ABC, if P is any point interior or exterior in the plane of the triangle, then PA square plus PB square plus PC square equals to GA square plus GB square plus GC square plus 3 times PG square will come. A relation between, easily we can prove by taking centroid, 3 vertices and randomly chosen some point alpha beta, and we can show that PA square plus PB square plus PC square will be given as GA square plus GB square plus GC square plus 3 times PG square. That's why here if P is any point randomly taken in the plane, sum of squares of its distances from the vertices is equals to, we are getting this result, and its minimum value, this 3 PG square minimum value is 0 when case P equal to 0. That's why this is greater than or equal to this value will come. That's why we get the inequality here, PA square plus PB square plus PC square greater than or equals to GA square plus GB square plus GC square. Inequality will be always applicable for any point in the plane of triangle. This is another important property in this here we have. Coming to one more important case here, let us concentrate on how to find the median in this triangle. If we have to find out median here, now let us see how to find the length of median in this triangle. To find out the length of median AD in a triangle ABC, we depend on two important theorems. One is the cosine rule from properties of triangles, or else the second one is the Apollonius theorem from pure geometry which is related to this median lengths. So here, if you are taking this Apollonius theorem, from Apollonius theorem, in triangle ABC, AB square plus AC square equals to twice we can prove it as AD square plus BD square. This is called Apollonius theorem, which can be proved by using pure geometry. In this method, if we are reaching this stage, now AB, this is taken as side C, AC with usual notation, this is B. This total length is A, this is A by 2, this is also A by 2. AD is our required length. Substituting all these in this, AB square is C square plus B square equals to 2 times AD square plus BD square is A square by 4. Now, transferring this all the terms other side, 2 AD square equals to, we are getting B square plus C square minus A square by 2. So, AD square equals to 1/4 of 2B square plus 2C square minus A square. Then length of AD equals to half under root 2B square plus 2C square minus A square. This is the way of finding length of median in a triangle ABC. In similar way, we can write two more medians also. Similarly, the second median BE equals to half under root. If you want the second median, here minus B square will come. Remaining will come here 2A square plus 2C square. And if you want CF, we can write it as half under root 2A square plus 2B square minus C square. Not only this, by taking these squares, we get one of the important interrelations between medians and sides of a triangle. Here, AD square equals to 1/4 of 2B square plus 2C square minus A square. If we apply sigma to this, here also we get sigma, then we get the relation by using this as AD square plus BE square plus CF square equals to 2B square plus 2B square minus B square. Finally, 3 times B square, 3 times C square, 3 times A square will come if you expand sigma. That's why we get the result as 3/4 of A square plus B square plus C square. This is the interrelation between sum of squares of medians and sum of squares of the sides. Not only this, even we can get relation between this and centroid related things also. Similarly, we can show that GA square plus GB square plus GC square equals to 1/3 of AB square plus BC square plus CA square. So like this, these two and these two are interrelated each other. This is the way of getting the connection between sum of squares of various cases in a triangle. So here, centroid is one of the most important concurrent points in a triangle, which is connected with various such interrelated relations in this triangle. Now let us focus on one more concurrent point in a triangle. Now let us see the other important points of concurrence in this triangle. Coming to these incenter and excenters, In a triangle ABC taken randomly, suppose if you are taking the internal angular bisector of A, this is A by 2, A by 2. Similar way, internal bisector of angle B, internal angular bisector of C, all the three we can show that they are always concurrent at a point which is denoted as the incenter of the triangle, which is equidistant from all the three sides of the triangle. This is always equidistant from all the three sides. So, taking this as center, distance to the side as radius, we can draw a circle. So, this circle is called as incircle and its center is called incenter, whereas its radius is called inradius. In similar way, if we take internal bisector of A and external bisectors of B as well as C, if you are taking these 3 points also concurrent at a point which is called excenter opposite to A. So, we can define in similar way excenter opposite to B and excenter opposite to C. So, 4 concurrent points related to these angular bisectors we can define in this triangle. Taking this IA as center, touching all the sides like this, we can draw a circle which is called first X circle or X circle opposite to A. In similar way, just we can draw X circle opposite to B, similarly X circle opposite to C also we can define. So, in any triangle we can define incenter as well as excenters. Now, let us see some more important points related to this incenter and excenters at a stretch here. If we draw triangle ABC in this, internal bisector of A, if we draw by using simple pure geometry theorems, we can show that angular bisector divides the opposite side in the ratio of other two sides. This BD is to DC equals to, we can prove it as AB is to AC, that is C is to B. This ratio we can prove it as C is to B. If the coordinates of this one are x1, y1, x2, y2, this one x3, y3, then coordinates of D we can prove it as bx2 plus cx3 by b plus c, by2 plus cy3 by b plus c. Now, on this internal bisector AD, somewhere if we choose I, we can show that this is dividing this in the ratio of B plus C is to A. If we take this section formula B plus C is to A and applying incenter formula will come as A x1 plus B plus C into this, B plus C cancel, bx2 plus cx3 by A plus B plus C. Similarly, we can show that y coordinate is A y1 plus B y2 plus C y3 by A plus B plus C. This is incenter formula. In similar way, if we produce it, somewhere if you imagine IA, we can show that this is dividing A and D in the same ratio B plus C is to A externally. Applying external section formula, we can prove this as wherever A is there, put minus A in the above formula, minus AX1 plus BX2 plus CX3 by minus A plus B plus C minus ay1 plus by2 plus cy3 by minus a plus b plus c. This is the way of getting external centers also. X centers opposite to A, opposite to B, opposite to C. These, if we observe closely, AD divided by I and IA in the same ratio, one internally, other one externally, and just now we have discussed that this type of points are called harmonic conjugates. Therefore, I and IA are harmonic conjugates to each other with respect to AD and vice versa. Here we have to recollect one more important definition. IA, IB, IC, these three will give us one more important definition. In a triangle ABC, if IA, IB and IC are X centers opposite to ABC respectively, joining these we can get a triangle which is called the eccentric triangle of the given triangle. Triangle IA, IB, IC is defined as the eccentric triangle of given triangle ABC, and this eccentric triangle is related to one more triangle in the triangle we define a next concurrent point, that is the pedal triangle. We discuss about this one in the coming concurrent cases.